Hello everyone, this is Vijetha, Associate Professor from the Department of ECE, MLR Institute of Technology. Today, I would like to discuss a stable multivibrator from linear and digital integrated circuits. I would like to talk on basic square wave generator circuit and working of a square wave generator, and I would like to talk about the period and that is time period, and I would like to discuss or determine the time period and frequency of oscillation for a square wave generator, or we can say that a stable multivibrator. Generally, multivibrators are a regenerative circuits which are mainly used in timing applications. And a stable multivibrator is a square wave generator. And a stable multivibrator toggles between one state to other without influencing any other external control signal. It is also called as a free running multivibrator, which also called as a square wave generator. This is a circuit for a stable multivibrator, or we can say a square wave generator. The output of an op amp fed back to a positive terminal. The output of this circuit has been fed back to the positive terminal of an op amp, and the resistors R1, R2 forms a voltage divider network. The beta here produces a value of R2 divided by R1 plus R2. The output will be either plus beta Vsat or maybe minus beta Vsat, that is saturation constant, positive value and negative value based on the input voltage which is producing at the negative voltage, where Vc is the voltage across the capacitor which is given to a negative terminal of an op amp, and where this Vc, if this Vc exceeds the reference voltage, this is the reference voltage, when the Vc exceeds the reference voltage, there will be a change in V0 as minus beta Vsat. To understand the operation of the circuit, let us consider initially the output is plus Vsat, the output of the circuit is plus Vsat, and the capacitor C, which its voltage shown as Vc, starts charging through a resistor network. The voltage across the Vc starts charging through the resistor towards the plus Vsat, that is when it is plus Vsat. The voltage at the positive terminal is held at beta value, that is R2 divided by R2 plus R1. So, the voltage across the positive terminal will be given as beta into plus Vsat. The capacitor tries charge towards the plus beta Vsat. The capacitor starts charging towards the plus beta Vsat. When the voltage across the capacitor just reaches above the voltage across the positive terminal, the V0 changes to minus Vsat. That is, the V0 changes to minus Vsat. Now, when V0 changes to minus Vsat, the voltage across the positive terminal will be given as beta into minus Vsat. When the capacitor discharges towards the minus Vsat, when it is just below the positive voltage across the negative voltage across the positive terminal, again it moves towards the plus Vsat. This is how it rotates, it cycles, repeats to produce a waveform in such a way. The voltage across the Vc changes at negative terminal just greater than the voltage across the positive terminal, that is beta Vsat. The output shifted to minus Vsat. So, the capacitor starts discharging when it just reaches to Vsat. The capacitor voltage Vc now increases more and more, negative point C just exceeds minus beta Vsat. The output now switches back to plus Vsat. The cycle repeats, the same thing which I have explained here. Finally, I can conclude like V0 is equals to, when V0 is plus Vsat, the capacitor charges to plus beta Vsat, charges towards plus beta Vsat from minus beta Vsat, and the output voltage switches to minus Vsat. When your V0 is at minus Vsat, the capacitor C discharges towards the minus beta Vsat from plus beta Vsat, and V0 switches to positive Vsat when V0 switches to positive Vsaturation, and this cycle repeats for number of turns. So, now we will determine the time period and frequency of oscillation. The frequency of free running multivibrator is determined by charging and discharging the time period of capacitor between minus beta Vsat and plus beta Vsat, vice versa. The voltage across the capacitor is given as Vc is equals to V final plus V initial minus V final into e power minus t by Rc. Here, when your initial value is at minus beta Vsat, when your initial value is at minus beta Vsat, then your final value will be equals to plus Vsat. So, Vc, that is voltage across the capacitor, when your initial value is at minus beta Vsat, that is at this minus beta Vsat will be the feedback voltage, that is at a positive terminal. When the voltage across the positive terminal of op amp is minus beta Vsat, then the output voltage is given as plus Vsat. If you can substitute these values in this expression, you can write this as plus Vsat plus, in place of V initial you can minus beta Vsat minus V final can be given as Vsat plus Vsat e power minus t by Rc. If you can solve this, you can write this as Vsat plus minus beta Vsat minus Vsat e power minus t by Rc can be written as, you can take Vsat common here, you can write Vsat minus Vsat. If you can take minus Vsat common, we can write as 1 plus beta e power minus t by Rc. So, voltage across the capacitor is given at Vsat minus Vsat 1 plus beta e power minus t by Rc when the capacitor is charging towards the plus Vsat. Similarly, when the capacitor is charging towards the negative Vsat, you can write beta Vsat. So, the voltage across the capacitor can be given as Vsat minus Vsat 1 plus beta e power minus t by Rc when it is charging towards the, when the capacitor is charging towards the plus Vsat. At time t1, the voltage of the capacitor reaches to plus beta Vsat. So, the voltage across the capacitor will be beta Vsat. So, by substituting the voltage across the capacitor as beta Vsat, you can write the equation as beta Vsat is equals to Vsat of 1 minus 1 plus beta e power minus t1 by Rc. This can be solved as beta Vsat is equals to Vsat minus 1 plus beta Vsat e power minus t1 by Rc. Next, you can write this equation as beta Vsat is equals to Vsat minus of minus Vsat minus beta Vsat e power minus t1 by Rc. Here also minus Vsat e power minus t1 by Rc. If you can take Vsat common, you can write this as Vsat is equals to, if you can take this beta Vsat towards this side, you can write this as Vsat as 1 minus beta, and if you can take this Vsat minus Vsat e power t1 by Rc minus beta Vsat e power minus t1 by Rc to the left hand side, you can write it as Vsat into 1 plus beta e power minus t1 by Rc. So, you can write this equation as, if you can minimize this expression, you can write as beta Vsat is equals to Vsat minus of Vsat e power minus t1 by Rc minus beta Vsat e power minus t1 by Rc. Now, if you can take this beta Vsat to the RHS side, and if you can take minus Vsat to the LHS side, you can write the expression as Vsat into 1 plus beta e power minus t1 by Rc is equals to Vsat into 1 minus beta. If you can take this beta Vsat to the left hand side, if you can take this beta Vsat to the RHS side and minus Vsat e power minus T1 by RC and minus beta Vsat e power minus T1 by RC towards the LHS side, you can rewrite this expression as beta, you can rewrite this expression as Vsat into 1 plus beta e power minus T1 by RC is equals to Vsat into 1 minus beta. So, this equation can be written as 1 minus beta is equals to 1 plus beta e power T1 by RC. As this expression, again this expression, now you can write it as 1 minus beta is equals to 1 plus beta e power minus T1 by RC, minus T1 by RC can be written as, see here, e power minus T1 by RC is equals to 1 minus beta by 1 plus beta. So, T1 by RC, I am taking the negative value, can be given as 1 plus beta by 1 minus beta. So, T1 can be given as e power, so log of e power minus T1 by RC is equals to 1 minus beta by 1 plus beta can be given as, this e power can be given as logarithm and the minus I have taken. So, I have written as 1 plus beta by 1 minus beta. So, you can write T1 is equals to RC into log of 1 plus beta by 1 minus beta. So, by substituting beta value as R2 by R1 plus R2, you can write the expression as RC is equals to log of R1 plus 2R2 divided by R1. So, this is a time period for a half cycle only when the capacitor is charging. For full cycle, that is when the capacitor is discharging, also you need to consider for writing a time period which is given as 2t1. So, you can write this expression as 2RC log of 1 plus beta by 1 minus beta, which you can rewritten as T is equals to 2RC log of R1 plus 2R2 divided by R1 by substituting the beta value as R2 by R1 plus R2. So, the total time period of a square wave generator is given as 2RC log R1 plus 2R2 divided by R1, and the output is symmetrical waveform. The frequency of oscillation, that is, we know that F is equals to 1 by T, where we got the T value as 2RC log of 1 plus beta by 1 minus beta. So, the frequency of oscillation is given as 1 by 2RC into log of 1 plus beta by 1 minus beta. Now, let us consider as R2 is equals to this R3. You can write R2 is equals to R, that is the resistive network which we have connected to the feedback. If these two resistors are equal, then the beta value will be equals to 0.5. So, the time period value will be given as, see, 1 plus, you can write as 2RC log of, if the two resistor values, beta value, beta is given as R2 by R2 plus R3. When R2 and R3 are equal, you can write as 1 by 2, which is 0.5 will be the value of beta. So, 1 plus 0.5 by 1 minus 0.5, which is given as 1.5 divided by 0.5, which you can write it as 2RC log 3. The log 3 value will be taken here. And the frequency of oscillation is given as 1 by 2 RC log 1 plus beta by beta, which you can write as 1 by 2.2 RC. This time period will be equals to 1.1 into 2 RC. Yes, 1.1 into 2 RC, and this will be 1.1 into 1 by 1.1 into 2 RC. So, the time period is given as 2.2 RC and frequency is given as 1 by 2.2 RC. Thank you.